Hello everyone, my name is Zhihong Guo. Today I want to share a paper, Highly Sensitive Aluminum-Based Biosensor Using Terrible Phenol Resonance in Capped Nanostructures. It posted on the Scientific Report of Nature, and its impact factor is 4.6 in 2022. And here I have summarized some key points for this work. Uh, first, first one is metallic nanostructure-based surface placement sensors are capable of real-time, label-free, and multiplex detection for chemical and biomedical applications. The, uh, then the study of aluminum-based biosensor has attracted a large attention because aluminum is a more cost-effective metal and relatively stable. And by changing the height of the nanostructure and the thickness of the deposit metal film, the transmission spectrum can be modified. It can vary, it can vary from Wood's anomaly dimension resonance to an astrometric phenol profile and surface placement domain resonance. These experiments demonstrate the high sensitivity of capped nanostructures with a LOD down to 236 phenolgram per milliliter for the protein-to-protein interaction detection. And in this, trans I want to introduction for the SPR. SPR sensing is capable of sensitive, real-time, and labor-free detection for many applications. The majority of SPR sensors is such as AU and AG, because these materials have low optic losses in the visible and near infrared ranges, and the AU, the gold material, is commonly used for the sensor because of its high chemical stability. Yes. On the other hand, the AG silver is easy to oxide and unstable, but exhibits more narrow and intense placement resonance. To prevent the silver film from oxide, preservation the electric film such as silicon oxide or aluminum oxide. However, the high cost of these metals limit large-scale commercializations of plasmonic sensors. Recently, the study of nanostructure-based aluminum sensors have attracted a large attention because aluminum is more cost-effective material and relatively stable. Yes. So in this work, we will use aluminum nanostructure as a material. Yes. First, uh, periodic nanogroup of 16 nanometer in width, 100 nanometer in depth, and 470 nanometer in period were fabric, fabricated in a resist coated on a silicon wafer by using electron beam lithography. And the pattern were spattered with gold and then electron formed with Ni and Gu for producing a 250 micrometer thick metal mold with different heating temperature from 170 to 190. The nanostructure with different ridge heights from 35 to 75 nanometer were made. And At last, using ALD to deposit aluminum fins with different thickness from 42 to 81 nanometer on an imprint plastic substrate. The capped aluminum nanoslit array were produced. In, in Figure 2b, the optical image of the replicated nanostructure array on an A4 size polycarbonate film. There are 416 arrays, and the area of each periodic nanostructure is 5 times 5 millimeter square. Yes, and in this picture in Figure 3c, it shows a scan SEM images for the capped aluminum nanoslit with different ridge height from 35 to 75 nanometers. Uh, in Figure 3D, the AFN we using a scan rate is 0.8 Hz, and the scan size is 5 times 5 micron meter square. The figure shows a AFN image of a capped aluminum nanoslit with different ridge height, and the ridge height are from 35 nanometer to 75 nanometers. And in this Figure 4a shows the optical image of array of capped aluminum nanoslit on a polycarbonate film. The insert in Figure A provides a schematic representation of the geometric parameter of the capped aluminum nanoslit, along with the polarization direction of the incident light. In Figure B, we show the major transmission spectra of capped aluminum nanoslit with a periodicity of 470 nanometers. The incident light is TM polarized, and measurements are taken in both air and water. And in there we choose height is 35 centimeter, T is 42 nanometer, W is 60 nanometer, and P is 470 nanometer for the nanostructure. In Figure C and D, we show the major angular transmission diagram of 470 nanometer period capped nanoslit array with 42 nanometer thick aluminum film in air. In in this picture, for various final factor, the surface sensitivity for spectral intensity change visibility. The maximum intensity sensitivity is 19% per nanometer is achieved when the final factor is close to minus 1.3. In Figure 4G, in Figure 5, the right side, illustrate a decay lapse for capped nanoslit with different final factor. Results indicate the peak resonance has a long decay less than deep resonance. However, when the final factor is close to minus 1.3, the deep resonance exhibits a significant shorter decay lapse of 242 nanometers, reducing it by a factor of approximately 1.73 compared to the decay lapse. The theoretical decay lapse is 421 nanometers. Yeah. And in this conclu and this was conclusion. I summarized 3 points. We utilizing hard exposing nano imprint, lithography and thermal evaporation to fabricate low-cost, large area and sorry high sensitivity capped aluminum nanoslit on A4 size plastic film. Second, the TM polarization wave is capped aluminum nanoslit with a period of 470 nanometer, generated extremely sharp and asymmetric final resonance in transmission spectra. Uh, at last, the book is a wavelength sensitivity is independent of final factor and mainly determined by the period. Nevertheless, the surface sensitivity is close relative to final factors. There's a reference. Thanks for listening.